morning. Once again I welcome you to this lecture, foundation engineering lecture. Today is the lecture number 9, and previously I have discussed about various aspects of shallow foundation and what is shallow foundation, what are the different types of shallow foundation, etc. Today I will try to discuss how the shallow foundation different computation, that means by bearing capacity, etc. How to find out about the theory of bearing capacity I will discuss, and maybe in this lecture I will be able to discuss one or two aspects. There are several aspects we will be discussed subsequently. So, let me go to next one that I have already discussed, that a strip footing, if it is loaded and then go up to the failure, then it is observed by Terzaghi that below the footing there are three distinct zones will be formed, and they are actually, one is this, that is called elastic zone or wedge zone, this is called radial shear zone, and this is actually Rankine's passive zone. And these three zones, and this is also geometrically perfect, that here it was shown 45 degree minus phi by 2, here actually angle was phi, and that phi is the phi of the soil. And for developing this bearing capacity theory, Terzaghi assumed several things, that one is that this is a shallow footing, and it is a base is rough, and this footing is rigid, and it is a continuous, that means strip type footing, and then finally supported on a homogeneous soil layer extending to a great depth. That means that there will be some influence zone. So, because of that, assume that there will be up to a sufficient depth the soil is homogeneous, and based on this assumption that bearing capacity theory was developed. And I can tell you one or two things, that when it is loaded from here and slowly increases, then this footing will have to tendency to go downward, and finally it may fail. And while doing so, what will happen, until unless this wedge goes down, that will not happen. And when this wedge will try to go down, then what will be there? This will be like one part, and it will have some resistance here and resistance here, because of this adhesion between the surface and also some pressure from both sides. So, that is the mechanism. That means, it will have before failure it will have an equilibrium because of this resistance here, and the weight of the soil and the load, all three together, it will be in a equilibrium position. Now, let me go to the next slide, where I will show that wedge only, and I will not show other parts, and how the equilibrium of the wedge considered in terms of, this is not shown, but in terms of their effect some force are shown, and then finally I will consider the equilibrium, and from there I will try to develop generalized bearing capacity equation. And you can see here that this is the wedge shown here, and you can see I can mark this one as A, this one as B, and this one as C, and this is the EBC triangular wedge, and Q is applied here, and suppose at failure condition, at just before failure I am considering the equilibrium. So, this Q become ultimate Q, and then this from this surface there is a adhesion, and this there will be resistance, vertical resistance, and this angle is phi, then and this width of the footing is B, and so that is this to this is that means over the width B, the load or pressure is applied, and other two zones are there which are not shown, but their effect are shown by these two forces. Now, if we consider the vertical equilibrium of this system, then you can see that Q u is applied over width B. So, Q u multiplied by B, and if I consider the unit length perpendicular to this, I take unit length of strip footing, then q into b into 1, I can say that become force, and pp from here 2 are there. So, 2 pp, and this one C force along this. So, if I take vertical component and then it becomes C sin phi, and since from two sides are there. So, 2 C sin phi, and if I consider this triangle, the volume of the triangle can be obtained, and that will be can be obtained easily, because half of this can be, and then half base into height is the area, and then multiply by 2, then become the entire volume, entire area, multiply by unit length, and then multiply by the gamma. And if we do that, then the weight of the soil in this ways become 1 by 4 gamma b square tan phi. So, that means this is actually acting downward and this is acting downward. So, this should be in same sign and these two are acting upward. So, this is the way vertical equilibrium of the system are considered. Now, C actually C to B, and that actually capital C, that actually multiply, again it can be converted in terms from the geometry, C multiplied by b by 2 by cos phi, and if I substitute in this, then q into b become 2 p p plus b c tan phi minus 1 by 4 gamma b square tan phi. So, this is one equation I have got. Now, I have to see still there are not in a convenient form. So, I will see next slide that you can see here that total force, passive force or total passive resistance P p on the surface A B and B C both side made up of the 3 components. Okay. And that 3 components are, one is actually called P p gamma, another is P p c, another is P p q. What is this P p gamma? This is actually is the force component which is coming from the shear zone, because of the weight of the soil. This is coming from the weight of the soil in the shear zone, and while I am considering this, assuming the soil to be cohesionless and neglecting the surcharge. So, that means when I will consider that part, that soil weight, then I will ignore other parts. So, 3 parts separately can be done. Similarly, PPC is the term which is actually coming from cohesion of the soil, and while assuming the cohesion, then soil to be weightless and neglecting the surcharge. This is also an assumption. So, only cohesion to be considered, and then only PPC. When only weight is considered, then PP gamma, and this is actually PPQ. It is coming from the surcharge, and when I will consider a surcharge, then I will assume soil to be cohesionless and weightless. So, independently 3 parts I can do, but finally after doing that I can superimpose, and then because of the superimposing, that error will not be much. So, that concept can be utilized. So, I can visualize P p in 3 component, P p gamma, P p c and P p q, and then if I substitute in that equation what I have got, then it will become something like that. You can see q to b, it will be remain unchanged, and this P p actually converted to P p q plus P p c plus P p gamma, and these are kept same. Now, I am introducing a new term that I will take 2 P p gamma minus this 2 P p gamma, 2 primes P p gamma minus this, that I will take together one part, and that I am giving a new term taking B 1 b outside and half gamma B n gamma. Similarly, I am taking 2 P p c, that means this plus this 2 together, 2 P p c plus this, I am giving a different name B multiplied by C n c, and 2 P p q, this part only I am giving another name B multiplied by Q n q. So, like that if I 3 parts ultimately this entire part, that means I had divided into 3 parts, and 3 part, that means if I do that, then equation will come something like that, q u b equal to your b multiplied by c n c plus b multiplied by q n q plus b multiplied by half gamma b n gamma. So, it will come like this. So, b everywhere common. So, if I ignore or remove from this, then the equation ultimately q equation equal to, it comes in the form c n c plus q n q plus half gamma b n gamma. So, this is the actually in between I have skipped several steps, because if you see the development of bearing capacity equation P P C N C N Q N gamma from the Terzaghi's theory, it will be a very elaborate and lengthy procedure full of mathematics. Perhaps we will not be able to go so much of details here. So, I will just try to given you the visualization how it has come, and finally, what is the final form of bearing capacity, that means Q ultimate equal to C N C plus Q N Q plus half gamma B N gamma. That means, for this is applicable for strip footing, because we have assumed the footing is a strip footing and it is on homogeneous soil, and of course, rough footing, then there are several assumptions was there. So, based on that we have got this, that means Q ultimate will be of summation of 3 component, one is this C N C, another is Q N Q, another is half gamma B N gamma. So, this is these 3 parts are called, this is called cohesion contribution, this is called surcharge contribution, and this is for weight unit weight contribution. So, 3 parts. So, this is the Terzaghi's bearing capacity equation for strip footing. Now, and these 3 N C, N Q, N gamma whatever we have taken, they are actually called bearing capacity factors, N C, N Q, N gamma, they are called bearing capacity factor, and one is N C is bearing capacity factor for cohesion, N Q is the bearing capacity for surcharge, and N gamma is the bearing capacity for unit weight. So, that is the thing, bearing capacity factor for cohesion, surcharge and soil weight respectively, which depend on friction. Again, this N C, N Q, N gamma, their relationship phi also given by Terzaghi. So, if you know the phi of the soil, then we can find out the N C, N Q, N gamma, and then using this equation I can find out the ultimate bearing capacity of the soil. And these are the final equation form, it is given by Terzaghi actually. N Q is e to the power pi tan phi multiplied by tan square 45 degree plus phi by 2. That means, if you just use phi in this equation, I will get suppose phi is 10 degrees, phi is 20 degrees, then what is the value of N Q I can find out from here. Similarly, N C is cot phi N Q minus 1. So, if again phi equal to 10 degrees or 20 degrees, from there you will get N Q minus 1 multiplied by cot phi will be your N C, and N gamma actually this is the one given later on by some other investigator, N Q minus 1 tan 1.45. This is actually not by Terzaghi, this was given later on by someone. Terzaghi initially given by the equation for N gamma by this expression, and this expression contains there is a K P gamma, which is very difficult to estimate. Actually, it is a passive earth pressure coefficient, depends on phi, actually has not given any some guidelines also given, but by using this whatever value we get, still Terzaghi value is little bit of conservative. Because of that, later on several investigators did, and then they have expressed the N gamma in this simple form. Okay, so, we will come later on, and of course, by using this we can find out N Q, N gamma and N C based on phi value, but Terzaghi. So, when Terzaghi developed this, actually we had difficulty to compute, even calculator was not there. So, he has followed some procedure and is given the value of N C, N Q, gamma for different values of phi in the graphical form and in the also in the tabular form. This is graphical form, that is also may not be exactly by Terzaghi, it is given by somebody, but it is also similar way. See, one axis is phi other axis is bearing capacity factor, and 3 curves are for 3 different aspect, that is NC, NQ and N gamma. And what is the when phi equal to 0, what is the value of NC, etc. will come later on, but these are the if you use graphical form, that means if you know the value of phi, then how to find out the NC, NQ and gamma. That suppose phi equal to 30 degrees, I will produce on this, on the 3 curves, I read this curve, all 3 curves, and from there I can get the NC, NQ and gamma, and then NC, that NC, NQ and gamma I can put it in the previous equation, which is written as Q equal to C N C. That means Q equal to C N C plus Q N Q plus half gamma B N gamma, sorry, half gamma B N gamma. This equation if I put, then I will get the ultimate bearing capacity. Also this is the graphical form, then there is a in the form of chart. This is actually given by Terzaghi, and you can see for different values of phi and different values of NC, NQ and N gamma is given. You can see when phi equal to 0, as per Terzaghi, NC equal to 5.7, NQ equal to 1 and N gamma is 0. So, this is the value actually sometime we have to remember, though suppose for a particular value of phi, suppose 18 degrees, you cannot remember these 3 values. You have to provide the chart if you want to calculate bearing capacity, but when phi equal to 0, what is the value of NC, what is the value of NQ, what is the value of N gamma, you cannot expect that this should be given. So, in the table, the top of the table, when phi equal to 0, that means NC equal to 5.7, NQ equal to 1, that means what? Phi equal to 0 means what? It is a purely cohesive soil, and when cohesive soil, then your NC value will be there, NQ will be only 1 and N gamma will be 0. That is the thing one has to remember. And subsequently, if the phi value changes, then how your NC, NQ value changes, that is the thing is given up to 50 degrees actually is given. Here I have shown up to 48 degrees. So, different books, if you see this table is also given. Some books it is given in the interval of 5 degrees, some are given 2 degrees, here actually every degrees values are given. So, this can be used for calculation purpose. And the bearing capacity, actually see the equation of bearing capacity is shown is applicable for both cohesive and cohesionless. So, generalized equation we have given, that is whatever equation, once again I can write here, that Q equal to C N C plus Q N Q plus half gamma B N gamma. So, this is actually generalized equation, and you can see dense sand and steep clay, as I have shown previously. Dense sand I have not discussed whether it is steep clay. For dense sand actually it generally fail in general shear failure, whereas loose sand and soft clay it fail in local shear failure. Okay. And so, this is actually for this equation developed for general shear failure. So, if local shear failure happens, that means when the soil is loose, then what equation will be used? Here there also the same equation will be used, but replacing some of the parameters by something. So, this in the latter case, that means the loose soil, the term C will be replaced by a C dash, C will be replaced by C dash, and that C dash will be what? 2/3 of C. When the soft soil, then same general shear bearing capacity will be used, but C dash will be 2/3 C. This is the modified value will be taken. Similarly, NC, NQ, N gamma, there are 3 terms. Those NC, instead of NC, NQ, N gamma, that will be taken as NC gamma, NC dash, NQ dash and N gamma dash. So, these 3 factors will be used, and these factors also can be obtained from the same chart with modified value of phi. Suppose the soil has phi equal to 20 degrees, then what I will take the phi will be nu phi, phi dash will be calculated by this equation. That means, same bearing capacity equation, only thing what I have to do, if the soil has a value of C, then the C will be reduced to 2/3 C, C dash will be that will be, and if the soil has value phi, then phi will be reduced to phi dash, which will be equal to given by this equation tan inverse 2/3 tan phi. So, after getting the reduced value of phi dash, then refer to the either to the table or chart and get the value of corresponding N C dash, N Q dash and N gamma dash, and then use same value, same bearing capacity equation. That means, it will be then C dash, N C dash, N Q dash, N gamma dash, and that to be obtained, and then you will get the whatever value will get. Obviously, the value ultimate bearing capacity will be much smaller than if I use the actual value of phi. So, this is the one way actually. So, separately for local shear failure, what will be the bearing capacity equation is not developed theoretically. Only thing, based on general shear failure, some modification is introduced to find out the bearing capacity of local shear failure. That is the only, and what is this modification? C will be reduced to a 2/3 C, and phi will be reduced to phi dash, which will be given by this equation. So, that is the only difference which can be used. Now, you can see as I have mentioned that the equation whatever we have suggested or whatever developed by Terzaghi originally, it is taken by initially footing was strip footing. That means, that bearing capacity equation was for strip footing, but this bearing capacity also was extended to different other footings, like when the footing is circular, then your bearing capacity equation was 1.3 CNC. So, this is the one term added here, and here 0.3 B gamma N gamma. Here actually it was half, it was half means it was 0.5, instead of 0.5 it become 0.3, and when it was a strip footing, the B was width, but when it is circular footing, B is the diameter of the footing. So, there are changes in two places. One is this one factor 1.3 in the cohesion part has come, and instead of 0.5 it came 0.3, the 0.5 reduced to 0.3, and the B is width of the footing, instead of that it is become diameter of the footing, that is for circular footing. Again same bearing capacity equation extended to square footing also. Here also same thing, 1.3 is introduced at this cohesion part, and here instead of 0.5 again it is 0.4. So, that means 0.3 for circular, 0.4 for square and 0.5 for strip. This is the easiest way to remember, otherwise B gamma N gamma, and when it is square footing, B is the dimension of the footing, both sides are same. So, dimension of the footing. So, these are the modification for other shape of the footing. For circular and square, of course, for rectangular footing sometimes it is a too long footing, then strip footing equation can be used, and when it is a suppose rectangular footing or aspect ratio 2 or 3 or 4, then rectangular equation can be used. So, with some modification that I will discuss later on, and in some book of course, sometime instead of 1.3 they use 1.2 actually, sometime to make it conservative actually. Instead of 1.3, sometimes people use 1.3, so 1.2. That means, we can, if we reduce the bearing capacity, we are in the conservative side. Now, I will try to see some more aspect. You can see for we have got the generalized equation Q u equal to C n c plus Q n q plus half gamma B n gamma. So, this is the general equation. Now, I will try to modify it for different soil. Suppose it is a purely cohesive soil, then what will happen? purely cohesive soil, that means phi equal to 0, and there I have seen that N c equal to 5.71, N q equal to 1 and N gamma equal to 0. So, when N gamma is 0, that component becomes 0. So, your equation reduces to C N c plus Q N q, and further this equation can be reduced to C means it will be N c means it is 5.7 C plus Q N q means again Q N q is 1. So, ultimately we can say the equation will be reduced to this form. So, when the soil on the footing a square on a steep footing on purely cohesive soil, then ultimate bearing capacity can be straight, can be either one you can go by this universal or generalized bearing capacity equation and modify for based on phi equal to 0, put this value and then come to this, or directly you can remember try to do 5.7 C plus Q. This is the ultimate bearing capacity on cohesive soil. Similarly, when it is a cohesionless, that means C equal to 0, but phi is having some finite value. In that case, when C equal to 0, then your this part will become 0. So, that will not, then your equation will be reduced to Q N q half gamma B n gamma. Here actually depending on value of phi, you can find out what is the value of N q, what is the value of N gamma, and then you can find out the value of bearing capacity. Now, further modification can be done. Suppose the footing initially was here, that means it is there was a d depth, then that was q equal to gamma times df. So, q can be replaced like this, that is the equation can be used here, but now I can imagine that footing is on the surface of the ground. In that case, for cohesive soil this component also will become 0. So, ultimately for surface footing on cohesive soil, your q u equal to C N c or 5.7 C. Similarly, if it is a surface footing on sand, then your C N c becomes 0, but these two parts will be there, and you can see then again if it is surface footing, q is 0. So, this part also will be there. So, this equation will be reduced to half gamma B n gamma. So, that means a footing on the surface of a cohesive soil, then directly bearing capacity is this, and a footing directly on the cohesionless soil, on the surface of the cohesionless soil, then directly you can remember the bearing capacity equation for steep footing is half gamma B n gamma. Now, if phi equal to suppose 30 degrees, then refer the table, find out the n gamma, then put it in this, then you will get the ultimate bearing capacity. Okay. So, these are that means generalized bearing capacity, if you remember, then you can modify depending upon the condition given. Suppose if it is a cohesive, then C will be there, phi will be 0 and corresponding N c N q N gamma you know. Similarly, if it is on the surface, again surcharge will be 0, then further modification will be there. So, ultimately reduce it to this, and similarly on the sand it will be reduced to this. So, like that one has to remember. Now, let me take one problem. You can see a strip footing is given suppose, and it is embedded at a depth of 0.6 meter and width is 1 meter, and unconfined compressive strength of this soil is 140 kPa and unit weight is 21.8 kilonewton per meter. Groundwater, I forgot, I missed that point actually. When the Terzaghi bearing capacity theory was developed, then they have considered water table is at a great depth, so that its effect will be ignored. So, water table effect is not there. So, here also groundwater was not encountered during subsoil, that means water table is much deeper and depth of the footing is 0.6. Now, we have to find out ultimate bearing capacity of this footing, an allowable wall load using factor of safety of 3. So, there are different types of bearing capacity. I have only discussed ultimate bearing capacity, there are net bearing capacity, there are allowable bearing capacity, we will discuss later on. For the time being, I will try to find out ultimate bearing capacity, and then if I introduce factor of safety 3, then what is the bearing capacity, that I will try to show. Now, for this footing, actually you can see, since it is a steep deposit of clay, that means your phi is 0, then your Q become CNC plus CNC plus Q NQ. Okay. This equation is there. So, your C is how much? When unconfined compressive strength is given, that is actually unconfined compressive strength QU, and what is the relation with the C? C will be equal to QU by 2. So, that means 140 by 2, that means 70. So, this becomes 70 and your NC become 5.7 and plus Q become how much? 21.8 is the unit weight gamma multiplied by depth equal to 0.6 and NQ is 1. So, if you calculate this one, we will get the value of ultimate bearing capacity. Okay. And I have not calculated that, you can calculate that. Once you get that ultimate bearing capacity, then you can find out allowable wall load. Allowable wall load means with respect to so, if it is the ultimate load, suppose on ultimate bearing capacity and it is, if I consider unit length, then that means this multiplied by 1, this multiplied by 1 will be load, ultimate load on the wall. This is ultimately ultimate load on the wall, ultimate load on the wall, and then what is the allowable ultimate load on the wall? That I can say this is a multiple, this become Q u, and what is the Q allowable? Will be Q u divided by factor of safety, that means Q u divided by 3, whatever value it comes, that will be your allowable load on the wall per meter length. So, this is the simplest possible problem I have taken. I will take some more problems, some other aspect also I will discuss one by one. So, this is one actually so ultimate bearing capacity of steep footing, and then for various condition how to modify, all those things I have discussed, and with this I will stop today. Maybe in the next class I will discuss some other aspect of the bearing capacity. Thank you.